Yo, what's up, class? Alright, got another big topic today. The chain rule. Applies to derivatives. Kind of one of our last big rules for dealing with more and more complex derivatives, right? Mainly we're going to be using kind of an expansion of the power rule to deal with, again, like I said, more complex functions. As always, give you some textbook definitions, some ways I like to think about it. Then we'll do some examples, and that'll be probably a little bit of a shorter video. But yeah, I have to have the light on here, so I'll try to stay away from the center of the board. I'm also trying out a new kind of video and audio setup. If it doesn't work, I'll revert to my old setup, but we'll see if this one is better. So, alright, chain rule. Allows us to deal with these things called really like nested functions. You'll see in a second. Textbook definition. Let's say we have f of x equal to something, right? And g of x equal to something, right? Now, let's say that something is equal to u for g of x, right? And also, now let's say these are both differentiable. Since they're differentiable, they're continuous, remembering to that video. Okay, we could do the whole limit proof. I'm going to skip that for now. We don't need it. We're going to say that, again, since it's differentiable, derivative of f exists, derivative of g exists. But what if we have a function of f of u, or which is also equal to f of g of x, right? So we have kind of a composition there, right? Now, what happens if we do f prime of u, which is equal to f prime of g of x? Okay, this is what the chain rule is describing, because it's a bit of a more complicated step when we have these composition functions, right? F prime of u here is actually going to equal f prime of x times u prime. Weird to think about that, but give you an example here, the way I think about it, that makes a bit more sense. Same thing over here. This derivative is going to equal f prime of x times g prime of x, right? Now, the chain rule, we're going to kind of go outside to inside. We start off with our normal derivative of f of x, and then kind of at the end of things, we're going to multiply by the derivative of the inside, the composition there. Now, the way I like to think about this, I think the way I'll express it over here is, let's say f of x is equal to x squared, right? That is a 2 up there in the exponent, x squared, right? Now let's say g of x is equal to x plus, 2x plus 4, right? Okay, now I'm going to draw it down here. F of g of x is equal to 2x plus 4 quantity squared. Now, what is f prime of g of x? Right? What is f prime of this whole function? It's going to be equal to, okay, we're going to do the normal power rule first. It's going to be pretty simple, actually. Bump this power out in front, and we're going to leave g of x, that internal composition function, as normal. And we're going to subtract 1 from the power like we do in our power rule. But I'm going to kind of draw a little squiggle under this to represent the chain rule, right? We're going to multiply by g prime. This is g of x in here. Remember that. So we're going to multiply by g prime times g prime, which is going to be, using our power rule, just 2, right? Because I took the derivative of this inside, that's in parentheses. Okay. Now let's go all the way back. Let's say this f of x function is equal to h of x, right? This is equal to h of x. So it's the same thing. We don't have to worry about composition functions. Composition functions are a great way to teach the chain rule, but the chain rule applies to every single function, right? So if h of x is going to be equal to that 2x plus 4 squared, right? The derivative, h prime, is going to be the same thing. It's going to be that, sorry, my handwriting's a bit out of control. It's going to be that 2 times 2x plus 4 times 2. And that simplifies down, right? But yeah, you see that there. chain rule applies to all functions, not just compositions, right? So I'm going to erase all of this. Sorry if it's a bit hard to see. Let the lighting shift there. We're going to do some examples because really the chain rule it's just going to become part of our like repertoire of tricks that we can use for derivatives. It's not super complicated, but it's also it's something we always have to remember to do. It's really, really easy to forget the chain rule. I have some, oh, I erased some examples, didn't I? Okay. Going to first start out with an example kind of on this side of the board here of g of x equal to, and then let's go with 6 times 4x. Start off with simple examples, plus 1, and then cubed, right? Now we're going to do g prime of x. It's going to be equal to, get out the red pen here, going to bring this power over, just like we do for our power rule, go outside from inside. It's going to be 18 times 4x plus 1 squared, because we subtract 1 from that power. Okay, and now we have this kind of internal function here. So it's just going to be multiplied by and then 4, right? That's it. That's the whole chain rule. You can always think of it. We go back up to this u example. I gave this u example here because you could say that g of x is equal to 6 times u cubed, if this makes a bit more sense to you, if u is equal to 4x plus 1, right? So then it kind of, looks more like your power rule that looked more like, 6u cubed. That's a more kind of, it's a simpler way to look at it. And I don't generally like to use this kind of substitution technique. We will have to use it much down the line in calculus, but for now, you can kind of just think of the chain rule as a big, step, composition functions intertwined, and we have to remember kind of to go outside from inside. So, go on to a more complicated example now. I'll also do it on this side of the board here, right? This time I'll choose kind of a rational function. I think we're going to go with 3 over, let's go with 3x plus 1 again, and that'll be our function. That'll be our function h of x, right? Sorry if that h is a little bit difficult to see. That's h of x there. Okay, now I'm going to rewrite this function. I'm going to say h of x. You'll see why now in a second. I don't really want to use the quotient rule here. Trying to use the product rule and chain rule at the same time, or the quotient rule and chain rule at the same time, is usually pretty difficult. And I strongly suggest you try to avoid using 2 of those rules at the same time, because remember, all of your derivative rules apply for the chain rule. So if, for example, there's a product inside this kind of composition function here, you got to do the product rule. Be warned, it can get pretty messy pretty fast. The chain rule leads to some very, very wacky functions. So I'm going to say that, Goose, stop that. Sorry, cat's getting in the way. I'm going to say h of x is equal to 3 times quantity 3x plus 1 to the negative first power. Right, kind of running off the board here, but really I just flipped this up and then changed that 1 exponent to a negative 1 exponent. Again, this is a negative sign right there, right? Flipped over the fraction. So now, h prime of x is going to be a little bit easier, since now we can just use our power rule, but with a negative exponent, right? So we're going to bring that out front. Negative 3 times 3x plus 1. Remembering to subtract 1 from our power. So all that to the negative second power. And then, kind of out of space. But I'm going to multiply that function by 3 because we have this chain rule here, right? Derivative of 3x plus 1 is just going to be 3. Derivative of that constant is 0. Derivative of 3x is just 3. So starting off with simple examples here, but eventually probably I might use another video to go into more complex examples because the chain rule is really going to follow us for a very, very long time. It's one of those rules that you have to think about more, and it's going to create some more complicated functions. Right, now, I'm going to simplify this down a bit. I'm going to multiply these 3's together, and I'm going to put this kind of exponentiated term or polynomial term on the bottom to get a positive exponent. It's going to be 3x plus 1 squared. Right. So that's our final answer there. With the chain rule, we turned this h of x function to that h prime of x function, derivative, slope. So, all in all, probably, again, like I said, come out with another video doing some more complicated examples, maybe using the quotient rule and product rule with the chain rule, because that's something you'll probably have to do especially if you're in like a class of calculus, right? Not just learning all of this for fun. But anyways, thank you very much for joining me to learn the chain rule today. Really hope you enjoy. This is a more complicated topic. It's kind of difficult sometimes to remember the chain rule. Can kind of sneak its way into a function through this composition kind of method here. But general advice, usually parentheses mean chain rule. Usually fractions mean the chain rule. Kind of binomial terms. We've been using binomials here for all of our examples. Trinomials, all that stuff. And chain rule, we could, like if I go back to our other example, we used something 2x plus 1, I believe, to the 4th power maybe, or 3rd power. Could have factored all of that out with like Pascal's triangle from a very long time ago. I don't want to do that though. Even Pascal's triangle takes a long time, right? You gotta draw all of that out or memorize it, which I don't suggest. Could just use the chain rule. Chain rule accounts for all of this, accounts for all of your nested composition functions. If you want to think about the substitution method, you can. That kind of simplifies things down, makes your functions look more like a basic power rule derivative. And again, if you can, at all costs, try to avoid quotients and products when you're dealing with chain rule. It's going to get very, very messy really fast. Yeah. Thank you very much for joining me in class today. See you in the next video. Goodbye.